Hi everybody, welcome to the beginning of the last unit of AP Physics C, Electricity and Magnetism. I divide my courses into 5 units, the first being about electrostatics, and the next being about Gauss's law, the third being about the electric potential, the fourth being about electric circuits, and then the fifth being electromagnetism. And the start of that unit is all about the magnetic field. So magnets are things that you've played around with since you are children, and you notice that sometimes they repel each other, sometimes they attract. And you've probably heard that opposites attract and likes repel. Well, that's true for magnets just as it is for electric charges. So we divide a magnet, instead of calling the ends positive and negative, we simply call it a north pole and a south pole, mainly because of tradition. And two north poles repel, two south poles repel, but a north pole and a south pole will attract each other. When we talk about a magnet in terms of its poles, the part that we call the north pole is actually really the north-seeking pole. So when we talk about Earth's north pole, technically that's a south magnetic pole, because a north pole of a magnet is what ends up getting attracted in that direction. Now, something else to keep in mind about magnets is that you can continuously just keep cutting them in half, and each time you do so, you'll get a north and a south pole. As far as we have ever been able to find experimentally, we have never been able to isolate a magnetic monopole that is just a north pole or just a south pole, and that's it. Now, physicists, at least most physicists, do believe they exist somewhere, somehow, just that they are extremely rare. And if you find one, in addition to getting an A in this class, you will also get a Nobel Prize if you are the first to find it. So, if an object that is not itself a magnet is attracted to one end of a magnet, then it will also be attracted to the other end. In other words, an object that's magnetically neutral that is attracted to either end of a magnet will be attracted to the opposite end. Here is the diagram of Earth as essentially a giant bar magnet. The idea is that we have this convecting core that is very conductive, and the convection helps to create a various series of currents that leads to a magnetic field. But notice that it's the south magnetic pole that is pointed up in this case, creating a magnetic field that's basically encircles our planet like this. Notice these little arrows. These little arrows are magnetic compass needles, and you know how typically the red end is what points north. Well, the red end is a north magnetic pole, just as the red end of Earth's giant bar magnet is a north magnetic pole, but it's actually toward the south geographic pole. Notice that they are not perfectly aligned. In general, a planet's magnetic field is not necessarily perfectly aligned with its axis of rotation, so that's just something to accept. And they might not even be concentric, so to speak. In the case of Earth, the center of Earth's magnetic field actually is pretty close to the center of the planet. But in the case of, say, planets like Mercury or Neptune, that's very much not the case. But in any case, notice that, again, the north pole of a magnet points toward Earth's north geographic pole, making it a south magnetic pole. Now, something else that comes up about Earth's magnetic field. I should mention something that we'll get into in more detail soon. The units of magnetic field strength are called teslas, not the car, but they're given by the symbol capital T, and a 1 Tesla magnetic field is quite a strong magnetic field. That might be pretty similar to what you get with some of those strong neodymium magnets or something like that. Earth's magnetic field is much smaller than that, and magnetic fields that are commonly encountered in astrophysics are typically a lot smaller than that, unless you're talking about neutron stars. So we've devised a smaller unit of field strength called the Gauss, where by definition a Gauss is 1/10,000th of a Tesla, 10 to the minus 4 Teslas. The reason this is particularly convenient is because Earth's magnetic field strength is about half a Gauss. It ranges from like 0.3 Gauss to 0.6 Gauss, depending where you are on the planet. Now, the fact that Earth has this ambient magnetic field, whose field strength is approximately half a Gauss, that is about 5 times 10 to the minus 5 Tesla, that is something that comes up on the AP exam, especially lately. And it could come up either on the multiple choice part, where you need to pick the best explanation for something, or on the free response part, where you need to give an explanation for like why people's measurements of this magnetic field of a current carrying wire are continuously off no matter how they orient it. It's something that does come up. And understanding and processing the fact that, hey, we have this ambient field strength of about half a Gauss, that is 5 times 10 to the minus 5th Tesla due to Earth's magnetic field, is quite important. So keep that in mind. It was discovered in the early 19th century that a current carrying wire will cause compass needles to deflect. In other words, moving charges, that is currents, create magnetic fields. In other words, a changing electric field will create a magnetic field. Now, if you're thinking, oh, what does that mean? A changing magnetic field would create an electric field? It does. That's where we really unify electricity and magnetism, but we're not going to get to that for a few more discussions. In fact, that's the Chapter 34 discussion. But in any case, these compass needles will point in the direction of the magnetic field, and the result is that you realize, okay, the magnetic field actually encircles the current carrying wire. In fact, the direction of the magnetic field, which is what we would call the north direction, that's the magnetic field points in the direction that would be kind of like the north end of a compass needle. That's what we call the positive direction, the north direction. That is given by imagining grabbing the wire with your hand, assuming that it's well enough insulated, such that your thumb is pointing in the direction of the conventional current. And when that happens, your fingers will curl in the direction of the magnetic field. We're going to have more to say about this when I show you a picture in just a second. Now, how this happens is given by something called the Biot-Savart Law. And we're going to have more to say about that later in this video as well. But a point charge can be used, a moving point charge will create a magnetic field. And here it is. This is the situation of a magnetic field being created by a moving point charge. Notice that the magnetic field strength, the symbol for magnetic field is capital B. It is a vector, so B vector. It has something to do with the speed at which the charge is moving. In other words, the faster the charge is moving, the quicker the electric field is changing at a location, and therefore the stronger the magnetic field. It has something to do with the strength of the charge. In other words, twice as much charge that's moving will give you twice the magnetic field strength. And it has something to do with the orientation between the direction the charge is moving and where you are trying to measure the magnetic field. That's where this cross R hat comes in. It also has something to do with the distance. If you're far away, it's not going to be as strong. Now, these constants, well, you have a 1 over 4 pi, that's maybe not too surprising. This constant in the numerator here, this is a constant of nature. It is mu naught. It is what we call the magnetic permeability of free space. So, that language sounds a little bit familiar. We came across the electric permittivity of free space, epsilon naught, which was about 8.854 times 10 to the minus 12 coulombs squared per newton meter squared. Well, mu naught, as it turns out, is about 4 pi times 10 to the minus 7 newtons per amp squared. And when you work all that out with all these other units, you end up getting units of Teslas for your magnetic field strength. Now, it used to be that mu naught was defined to be 4 pi times 10 to the minus 7 newtons per amp squared, but now with the redefinition of various fundamental constants that occurred in May of 2019, I believe, it simply became about 4 pi times 10 to the minus 7 newtons per amp squared. But in any case, whether you're talking about or exactly, your answer will only be off by at like the 7th or 8th decimal place, or the 7th or 8th significant figure, so I wouldn't worry about that. We'll pretend that it's 4 pi times 10 to the minus 7 newtons per amp squared, and that's what I'm going to plug in when I plug in values for mu naught. Anyway, that is the Biot-Savart law in point charge form. So this unit vector r hat points from the charge toward the point whose magnetic field is being calculated. So we're going to look at some examples on this in just a minute. The direction is given by the right-hand rule. This is a cross product. So the idea is that whenever you have a cross product, you imagine orienting your right hand so that your palm so that your fingers are facing in the direction of the first vector, and you orient it so that as much as possible your palm is facing in the direction of the second vector. As much as possible, have your palm face the direction of the second vector, while your fingers of your right hand actually are pointed in the direction of the first vector. When you do that, and your thumb is extended out, then your thumb will point in the direction of the cross product, which in this case would be the direction of the magnetic field. So here's how that would end up looking. So there's the direction of the first vector, which for us is the velocity direction in the Biot-Savart law. And then again, you orient your palm as much as possible so the unit vector, the r hat, the palm is kind of facing that direction. And then when you do that, your thumb is going to be pointed in the direction of the magnetic field, the third vector. So in general, cross product, A vector cross B vector equals C vector, while your fingers will point in the direction of A vector. As much as possible, your palm will be in the direction of B vector, and then your thumb will be in the direction of C vector. The big point about the cross product is that the direction of the vector that you get from the cross product, okay, technically a pseudo vector, the direction of the thing you get from the cross product is perpendicular to both of the vectors that go into the cross product. So what's also important about it is that the magnitude of the cross product can be expressed as the product of the magnitudes of the individual vectors times the sine of the angle between them. If the angle is 90 degrees, then the magnitude of the cross product is just the product of the magnitude of the vectors. And you're essentially dealing with a right triangle and a Pythagorean theorem type of thing. Now, with that in mind, you can think of the Biot-Savart law being written like this, as mu naught over 4 pi times qv sine theta over r squared. I think it's best to at least memorize the form that's in the cross product form, because that way you'll be able to, whenever you have some direction of motion, be able to use the right-hand rule quite effectively, as long as you understand that, hey, that r hat is going from the source charge, the point charge, to the direction where the magnetic field is being calculated. These units for magnetic field, well, you can remember the units of a quantity are on one side of the equation must be equal to the units on the other side of the equation. So we have this mu naught qv sine theta over 4 pi r squared. Well, we can plug in units for all of these. We have units for mu naught, those are newtons per amp squared. Units for charge are coulombs. Units for speed are meters per second. Oh, a coulomb times a meter per second, that's called an amp. A coulomb per second is called an amp, and a meter cancels with a meters in the denominator. So now you get newtons per amp meter for your units for magnetic field. Well, understandably, people decided that that needed its own name, so we call it a Tesla. But a Tesla is a newton per amp meter. And again, commonly used units that are non-SI units are field strength of Gauss, where Gauss is 10 to the minus 4 Tesla. Okay, so let's take a look at some examples where we apply the Biot-Savart law for situations involving moving charged particles. And again, I would recommend memorizing the law at least in its cross product form, and maybe even also the mu naught over 4 pi times qv sine theta over r squared. Understanding it's a 1 over r squared law helps, and remembering that back with Gauss's law and Coulomb's law, we had a factor of 1 over 4 pi epsilon naught that we called that k. Well, now the factor out front is mu naught in the numerator, this time over 4 pi, and we have a qv sine theta in the numerator as well. Now, another big thing to keep in mind, and they love pulling this trick on the multiple choice part of the AP exam, they'll deal with a charge that's negative. Well, if the charge is negative, you're going to need to reverse the direction of the magnetic field, because your Q is negative. So you have a negative Q in there, everything's going to be negative. So just keep that in mind. So they'll say something like, an electron is moving through a field. It's like, oh yeah, that's right, an electron is negatively charged. Okay, so here we go. This is a picture of a quark and her baby. It actually has nothing to do with magnetic field and stuff like that, but hey, who doesn't love quarks? All right, getting to it. Consider the Bohr model of a hydrogen atom where an electron circles the proton at a distance of 5.29 times 10 to the minus 11 meters, or 52.9 picometers if you prefer, or 0.529 angstroms. All kinds of funny units here. Calculate the magnitude of the magnetic field felt by the proton. The electron is moving around at a speed of 2.19 times 10 to the 6th meters per second. Okay, well, here we have our magnetic field equation, the Biot-Savart Law in angle form, where we turn that v vector across r hat into just a v sine theta. So we know what Q is. Q is the negative of the elementary charge, and the V is given. The angle is 90 degrees because at any one time, at least on average, the angle between the electron's direction of motion and the proton is 90 degrees. And the radius is the Bohr radius, 5.29 times 10 to the minus 11 meters. Or the distance, I should say, is the Bohr radius. Okay. So now that we have all that out of the way, we're going to realize that, okay, we're going to just be dealing with the strength of the magnetic field. So since all we want is the strength, we eschew negative signs and plug in our numbers. So I plugged in for mu naught, plugged in for Q, at least the magnitude of it. The angle is 90 degrees, so sine of that is 1, so that goes away. And we have a V, and don't forget about that 4 pi that was out there from the mu naught over 4 pi bit. And then the r squared. So after we plug that in, we get a magnetic field strength of 12.5 teslas. That's a pretty strong magnetic field strength. But hey, the electrostatic force there is also pretty strong. Now, the fact that there is that magnetic field strength has consequences for situations where light is encountering these atoms in other magnetic fields. Like if there's an ambient magnetic field, things are going to be shifted, so the wavelengths of the light will end up getting shifted as well. Zeeman splitting. Okay. Now, another example. Here's one where we're going to need to use the vector form of the equation. Determine the magnetic field at the point due to the particle in this picture. Express your answer both in vector form and in the form of magnitude and direction. Okay, well, our v vector, so this proton is moving in the positive j direction toward the increasing value of y. This is a normally oriented xy plane. So v vector is 2 times 10 to the 7 meters per second j hat. And r hat, our unit vector, well, how do you get a unit vector? You draw a vector from the point to where you are and divide by the magnitude of that vector. So something else to notice is that we have a different situation here. Did you notice that the point where they want to know the magnetic field is not at the origin? Yeah, of course you did. Right. Yeah, so the point where they want us to calculate the magnetic field is actually right here. It's not at the origin. Our unit vector is still fine, but notice that our r value is not just square root of 2 centimeters. It's different because we got to go from here to here. So imagine going 2 over here, 2 over here, 2 squared plus 2 squared is 8. And then don't forget you're going to have to take the square root of that to get r, but luckily we don't need to get r, we just need to get r squared. But in any case, yeah, when you convert this 8 centimeters squared into meters squared, don't forget that when you convert centimeters to meters, the conversion factor gets squared since the whole thing is squared. So, but the 8 does not get squared because we already did that in adding together the 4 plus 4. That's the Pythagorean theorem. So anyway, your r squared is 0.0008 meters squared. All right. Now that we've written our givens, this really shows the importance of writing givens, because when you're dealing with things that seem nasty because they're vectors, well, once you write down your givens in terms of those vectors, everything becomes fine. So you have your givens, and now we're ready to plug stuff in. Now, I plugged in all of the constants And I plugged in my charge, I plugged in my speed, because, oh, there it is, 2 times 10 to the 7 meters per second, and I left the vectors by themselves. All right, so let me just tell you something, and I'll then convince you that it's the case for our particular situation. It's something you should memorize. First, any vector crossed with itself is 0. After all, that would be a 0-degree angle, and sine of 0 is 0. Second, I cross j is k, where k is the unit vector in the z direction. J cross k is I, and k cross I is j. That's what we call the cyclic permutation. I cross j is k, j cross k is I, k cross I is j. As long as you're dealing with a cyclic permutation, the cross product is the next thing there. If you reverse them, I cross j is k, but j cross I is negative k, because after all, the angle now is negative 90 degrees. So, or you can think of the right-hand rule. If you reverse it, you're flipping your right hand upside down, since you got to go in the direction of the second vector now first. So the direction of your thumb is going to be flipped. So you get a negative sign. All right, now let's apply those rules here. Well, the distributive property works with cross products. That's nice. So j cross negative I, well, that's going to be the same thing as negative I cross j. Well, two negatives make a positive, so j cross negative I is the same thing as I cross j. Okay, so this first part is k. What about j cross negative j? Well, that's negative j cross j, which we know is 0, and negative 0 is 0. So all we're left with here is k. So there we go. We have a magnetic field strength there of 2.8 times 10 to the minus 17 Teslas k hat. Okay, so very cool example. Now, in terms of answering the overall question, the magnitude and direction of the magnetic field strength, if they wanted it as something related to the picture, that would be 2.8 times 10 to the minus 17 Teslas coming out of the page, directed out of the page. That is, if you're looking at the screen, it's directed straight toward your eyes. Now, the form of the Biot-Savart law that we will often use, well, sometimes it's just due to point charges, but a lot of times it's related to the current that is generating the magnetic field. Because remember, what Ørsted discovered was that a current-carrying wire will generate a magnetic field. So it turns out these equations are really exactly the same. It took a little while for me to become convinced of that, so finally I just kind of proved it to myself by thinking of, okay, let's start with the first equation, and then consider that QV term. That QV term, which is really the thing that changes between the first equation and the second equation, V is just delta S over delta T. In other words, how far something goes in a certain time interval, the speed. But we can rearrange this because, after all, if we're dealing with a continuous stream of particles, that's going to be a certain amount of delta Q that goes by in a certain distance. So it's a bunch of charges, delta Q, that move over a certain distance that we'll just call L. Okay, well, since V is delta S over delta T, and then we can think of that delta S as L if we're talking about a continuous stream, delta Q of charges that go by in a certain amount of time, delta T. Well, that works out. Q delta S is delta Q times L. So then we just rearrange that. We have delta Q over delta T. That's just the current I. So now this gives us the form of the Biot-Savart law that is typically seen in textbooks and other references. Now, as before, we often express this in vector form. So we can think of, okay, have a mu naught I over 4 pi on the outside, but this dl sine theta, that's going to be the dl vector, where L vector is the direction of current flow, cross r hat. And notice we have it's a dl because, like, it might be a curvy wire. So it's the direction of current flow at that particular infinitesimally small segment. Cross r hat, or again r hat, is the unit vector going from that point in the wire to the place where you're trying to measure the magnetic field. So keep in mind something else, that this form of the Biot-Savart law is actually only intended to be used when it's on the inside of an integral, where we also consider the right-hand rule when we're doing that calculation. So this is the form that you will most commonly encounter in physics problems on the AP exam. Every once in a while you might have to calculate it due to a point charge, but that's a bit rare. So when you're dealing with a 2D Cartesian plane, the directions are usually fairly simple to figure out, but for 3D applications, we're going to use, we need to think about the right-hand rule and add a couple of directions. So symbols for dealing with things going into the page or out of the page or something like that. If a vector is coming out of the page, it's indicated by a circle with a dot in the middle, kind of like an arrow coming right toward you with the point, the tip of the arrow being in the middle of the overall arrow. If it's going into the page that is away from you, it's kind of like looking down the tail of an arrow, like this. So it's like, you know, you're dealing with the feathers at the end of the arrow, so you're looking down that way. So the tail of an arrow flying away from you. Now, let's figure out what's going on with a straight wire. Pretty soon we're going to figure out the magnetic field strength due to a current carrying wire using this law. So if you could, first of all, in terms of the right-hand rule, if you consider a straight current carrying wire, then using the right-hand rule and kind of grabbing the wire, no matter where you grab that, the field is always going to be circling around the wire. Your fingers of your right hand are going to be circling around in the direction of the wire, kind of like this. So your thumb is pointed in the direction of the current, and your fingers are circling in the direction of the magnetic field. So that's how we kind of think of the right-hand rule when we're dealing with a current-carrying wire, and that's something that you should remember. And your fingers are curling in the direction of the magnetic field. In fact, that curl is the same idea as the curl that those of you who have taken multivariable calculus came across in talking about the curl. In other words, the magnetic field actually is the result of a curl, a vector curl. And that's something that we'll have a little more to say about when we talk about Ampere's law, which is actually derived from Stokes's theorem. Okay. So let's derive a formula for determining the magnetic field at a distance r away from a long current carrying wire I. I mean, after all, long current carrying wires are fairly common in physics and electronics, and so, I mean, this sounds like a pretty important problem, and it is. In fact, we're going to get a general result when we do that. So we're going to consider this figure where we are going to use the Biot-Savart law in current form, where we're looking at a current element that has thickness dx, that's at some distance x from our origin. And the idea is that we want to measure the field at this distance r above the middle of the wire, the distance r from its closest point to the wire. Okay, so what we're going to do is we imagine a current element like this, and we're going to calculate the magnetic field contribution due to this current element. And then we're going to add them all up in the form of an integral. So first of all, you're going to notice that there's going to be an x component and there's going to be a y component. So let's consider this, a ds vector cross curly r hat. Now notice that in this case, curly r is not the same thing as my distance little r from the wire. The distance little r is the perpendicular distance from the wire. Curly r is the distance from the field element to where I'm trying to calculate the field strength. So that's what's going to need to go in here. Be very careful with that. How do we get curly r? Well, again, you draw a vector from, at least an easy way is to draw a vector from where you are to where you need to go and divide by the magnitude of that vector, magnitude being given by the Pythagorean theorem. Okay, so where I'm at, to go where I need to go x to the right, and I need to go r up. Okay, there you see it in the Pythagorean theorem there. And looking at this, you might wonder, why is there a negative sign in front of my x here? Well, think about it this way. I mean, you're thinking, oh, I'm going over x and up r. Well, this needs to be a general form of my unit vector that would work for any value of x. Well, if I'm to the left of the origin, my values for x are going to be negative. Well, plugging in a negative value for x ends up giving you a positive value for the I part of your unit vector, which is exactly what we want. Yay! Okay, so now we have our magnetic field strength element in differential form from the Biot-Savart Law, the current form, where curly r squared is x squared plus r squared. And again, we want to add up all of these contributions at all possible points. So all possible points, if it's a long wire, that means infinitely long. When you hear long, that means infinitely long. So we need to integrate over all parts going from x equals negative infinity to infinity. So how do we express our ds vector across curly r hat? Well, ds vector is just going along the direction of the wire. So going in direction of increasing current, direction of conventional current, that's just going to be a dx times I hat. And our r hat is what we had before. It's right here. So, well, I cross I is 0, and I cross j is k. So there we go. We immediately got rid of a part just by doing this part separately. We got rid of something that looked rather nasty. Okay. Now, here's where we have it. Our magnetic field vector is given by this. Now, technically, this should be, I should probably call this, instead of r, I should call it a y at some distance y, because if y is negative, then that's going to give me a negative value, which is really kind of what we would expect. Now, we'll take a look at that later, but for now we're just looking at the magnetic field strength in general, so we could really probably drop the k here. So in any case, completing this integral, going from negative infinity to infinity, we're going to let, this is a typical trig substitution, we're going to let x be defined as r tangent theta, because the only place we have an x is down here in this 3/2 power thing. Now, again, this is really x is y tan theta, but whatever. So therefore, dx is r, or y, secant squared theta, d theta. So given that, we are suppressing our vector notation now. We plug in for our dx up here. There's our secant squared. And we plug in for our x equal r tan theta. And the whole point in doing that is because 1 plus tan squared theta, after we factor out this r squared, is secant squared theta. Secant squared theta to the 3/2 is secant cubed theta. And secant squared over secant cubed is 1 over secant. Well, 1 over secant is called cosine. And also notice that we have an r in the numerator here, 3 factors of r in the denominator, that's a 1 over r squared. Well, we also already had an r out here in front, so that becomes a 1 over r, because r over r cubed is 1 over r squared, r over r squared is 1 over r. Okay. So back in kindergarten calculus, you learned that the integral of cosine theta was sine theta. So we evaluate that, going from, and since we did our trig substitution, we think, okay, since x was r tan theta, so we said, okay, we need to think about what our our x going from negative infinity to infinity is. So that's going to mean that theta is effectively going to go from negative pi over 2, pi over 2. So it actually is kind of this angle theta right here. So all the way over here would be theta's negative pi over 2. All the way over here would be theta's pi over 2. In any case, sine of pi over 2 is 1, sine of negative pi over 2 is negative 1, and we get this result, that the magnetic field strength is mu naught I over 2 pi r. The direction is given by the right-hand rule. So if y is positive, going back to thinking of this as y. If y is positive, then it's going to be pointed out of the page. Well, out of the page is the positive direction. If you're thinking of a normal Cartesian plane with x to the right and y up, z would be out of the page. That would be the positive z direction. And if y is negative, well, the direction of your field would be negative. That would be into the page. So there we go. We're going to come back to this b equals mu naught I over 2 pi r bit later on in the unit. In fact, in another video in the same chapter. I'll just tell you that this result can be thought of as an early form of something called Ampere's law, which is one of the most important equations in this course. So just for now, I would memorize it, and then we'll actually use it for more applications later on. Ampere's law can be thought of this as the magnetic equivalent of Gauss's law. So in any case, here's our result if we think of this as a y instead of an r. So b vector is mu naught I over 2 pi y times k vector. In this situation, if a current carrying wire is going in the direction of the positive x-axis. Okay. So now, let's consider the magnetic field at any point along the axis of a ring of charge. Sorry, not a ring of charge, but a ring of current. We did ring of charge back in kindergarten E&M in the first unit. So derive an equation for the magnetic field at any point on the axis of a ring of radius r carrying a constant current I. You might wonder, like, how are you going to get a constant current I on this if you don't have a battery? Well, if there's some other changing electric field there, as we're going to get to later in this unit, that would create such a thing exactly. Okay, so anyway, how would we do this? Well, we consider a unit, a little bitty bit of current, in, say, this part right here of thickness ds. And here we think of an angle. The angle theta is the angle between ds and where we have our ring. But remember, what we mean by where we have our ring is where we have the current going. Well, the current is going along the ring. At any particular point, the angle between the direction of the current and the direction of our unit vector is 90 degrees. So it turns out that in this case, the sine of theta is 1. So in any case, we'll just call this distance r. So we don't need a curly r here. So r squared is x squared plus big R squared, where big R is the radius of our ring. So here is our Biot-Savart Law in this form. We have an I sine theta, and again, sine theta here is 90 degrees. Or sine theta is 1 because theta is 90 degrees. It's the direction between the unit vector and the direction of the current travel. But the current is traveling in a direction, no matter where we are, that's 90 degrees compared with our unit vector. Okay, so sine of theta goes away because it's 1. I like things that are 1. I like them even better if they're 0, except if it's a denominator. But what we need to do is we need to realize, okay, we need to come up with a new angle that we're going to call phi, that's actually going to be the angle around this circle. Well, ds is going to be rd phi, where ds again is the segment here. Big R is the radius of the circle, of the loop. So this amount, little ds, is going to be equal to, well, the radius of the loop, big R, times d phi. And we're going to add up all the contributions for phi, no matter where phi is. Luckily, there's going to be a great deal of symmetry that we'll be allowed to use. Now, just to make things a little bit easier, I'm going to define a new angle that I'm going to call eta between the unit vector and the x-axis. So for any particular value of x, that angle is going to be the same. So, and luckily, there's only one value of x right here. So, in that case, the tangent of eta, since tangent is opposite over adjacent, the opposite of this angle, again, the angle kind of, imagine a line going from our point to where we are. Eta would be this little angle right here between the axis and a line connecting the point where we're measuring the field with the current element. So opposite is big R, adjacent is x. So eta, or tangent of eta, is big R over x. Now, part of the point in doing this is that due to symmetry, all of the off-axis components of our magnetic field contribution are going to cancel during the integration. In other words, by off-axis, I mean, okay, due to this particular current element right here, there's going to be a component of the magnetic field that has a y direction and a z direction. Well, guess what? That's going to be exactly canceled by the component due to the ds that's on the opposite side of our ring over here. And what about at the top? Well, then there's going to be a component that's only in the negative y direction. Well, that's going to be canceled by the component that is in the y direction due to the ds at the bottom of the loop. So, since that's going to be a situation, and dB is perpendicular to our unit vector, the only thing we have left is the x component of dB that's really going to be dealing with. And the x component of dB is going to be found by thinking about the sine of this angle, eta. So here's an expression for that x component, where we just have r divided by square root of x squared plus r squared because of just the sine of that angle. It's the same idea as that eta. So here it is again, in case you don't believe what I was just saying. So this angle eta is what we're talking about, and then you imagine, okay, that's the same thing as this angle eta because of similar triangles, and the only thing that you're going to have left at the end is the sine of eta, because any part right here that's off axis is going to cancel with the stuff over here. Okay, so it's something to keep in mind though, because unless you're thinking very carefully about some of your angles, it can be easy to screw this up. I did the first time I did the derivation. Okay, so with that in mind, and having already plugged in for our sine of eta bit, the x component that's left over is this r over square root of x squared plus r squared times dB. And again, we're going to consider contributions from angles all around the loop, from here at phi equals 0, all the way around here to phi equals pi, all the way around here back to phi equals 2 pi. So, and that, once we get back to 2 pi, we will have gone all around the loop. Okay, so here is the expression for our x component of our magnetic field contribution due to some angle d phi, due to some angle d phi. So again, we need to add up all of those angles. And again, we already plugged in for the fact that we just want the x component. In other words, dB sub x is equal to dB times sine of phi, where sine of phi again is big R over the square root of x squared plus r squared. Okay, so while this looks really, really bad, we notice that the only variable that's in there is actually part of the differential, so we can pull everything outside of the integral. Mu naught I over 4 pi obviously goes outside of the integral, but so does the r squared over the 3/2 power of x squared plus big R squared. All we're left with is d phi, and we're integrating that from 0 to 2 pi, so that's just going to give us a factor of 2 pi. Well, I know what 2 pi divided by 4 pi is. That's a half. So there we go. That is our magnetic field strength along the axis of a ring of current. If it's off axis, I can't tell you, because you're going to be dealing with all kinds of weird integrals that won't cancel out and also are not solvable except numerically. So this works for any point along the axis of a current carrying loop. So it's a good result to kind of keep in mind. Now, I would not memorize it, because the only time you're really going to need it is when you need to derive it. Well, I don't know, maybe memorize it for the multiple choice part, because you might get something like this on the multiple choice part. I would think it unlikely though, so I mean, I would only bother memorizing it if you have extra time before the AP exam. The more common thing to encounter on the multiple choice part is asking about the magnetic field strength at the center of the current carrying loop. Well, at the center, x is equal to 0, and r squared is to the 3/2 is just r cubed, and you'll have an r squared over r cubed, so therefore at the center, it's mu naught I over 2r. So that is the part that's a lot more often encountered on the AP exam in the multiple choice section. My guess is that if you needed to deal with this result, that's not at the center but still on the axis, it would be on the free response part, and you would have to derive it just like what we did. Now, keep in mind that something we're going to encounter later on is situations where you have multiple loops of current, where you have wire loop, 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 loop. Well, in that case, you just multiply by the number of loops that you have, and your result will change accordingly. It's proportional to the number of loops you have, n. Okay, that is all we have to say so far. In the next video, we are going to examine how to deal with situations where your current is not of uniform density. In other words, at some points in your wire, you have the current maybe having a higher density toward the center of your wire and a lower density toward the edges of your wire. And that's where this result that leads to Ampere's law will become very, very important. So, hope to see you then. Comments and questions in the comments bar on YouTube, and thank you for watching.